So there is a charged metallic sphere of radius r, and the charge and the excess charge. So whenever I say charge, we almost always mean the excess charge is distributed uniformly on its surface. We've put some positive charge on our conductor, and it's going to go to the surface. And since it's a spherical surface, it will just arrange itself uniformly on the surface. So that's where we are right now. So we have positive charges on our spherical surface. Okay, now what's the question asking us to find? We have to find the electric field produced by this positive charge. That's our ultimate goal. So that's towards the end here. Okay, maybe I forgot to even put that as a question, but that's our ultimate goal. We want to find the electric field produced by these positive charges at a point over here, let's say, at a distance r from the center of the sphere. Now, calculating this electric field using the techniques of the last chapter would be very, very difficult. It's not impossible, but it would be very difficult. So the way you would do it is you would take a small section of the surface of this sphere, calculate how much charge there is in that small section, call that dq, then calculate the electric field produced by dq over here, dE or something, and then you would have to vector add the electric fields produced by all such dqs all over the sphere. So you'd have to do a surface integral over the sphere to get the net electric field at the point that you're interested in, at the point P. As I said, that's not impossible to do, but it's a very long and very, very tedious calculation. So we are not going to use that method at all. We are going to do it in a different way. So okay, so how do we do it? So let's look at, I've broken it up into steps for you. So let's try to answer each of these questions. The first question is, what kind of symmetry does this charge distribution have? So remember that the charge is now distributed uniformly over the surface of the sphere. So the three types of symmetry that we talked about in the last class, which one applies here?
Spherical.
Yes, the charge is distributed over a spherical surface. So that would be spherical symmetry. The charge distribution is spherically symmetric. Spherically symmetric charge distribution. All right. So if you have a spherically symmetric charge distribution, the electric field produced by that charge must have spherical symmetry as well. Why is that? Because the point of spherical symmetry is that you're not supposed to be able to tell if the system has been rotated, right? We discussed that yesterday. Suppose the electric field were not spherically symmetric. So suppose right now there is an electric field over here. There's an electric field over here, which is in this direction. But there's an electric field on the other side at the same distance, which is in a completely different direction. This doesn't make any sense at all. But suppose the electric field over here is in that direction, and the electric field over here on the other side is in a different direction. So now you can completely tell. So if you close your eyes and your friend rotates the sphere, you can completely tell that it's been rotated because the electric field is not spherically symmetric. So the electric field produced by a spherically symmetric charge distribution has to also be spherically symmetric. So the charge distribution is spherically symmetric, as I wrote. Distribution is symmetric. Spherically symmetric, all right, that's a lot of words. Spherically symmetric charge distribution. This implies that you have a spherically symmetric electric field. All right, next question is, what does that imply? What does that imply, or what can we conclude about the magnitude and direction of the electric field? So ultimately, the electric field is what we're trying to find at a radius r. So what can we conclude about the magnitude and direction of the electric field, given that it must be spherically symmetric? So one thing we can conclude about the direction of the electric field is that it must be radially outwards. So that's consistent with spherical symmetry. So the electric field must be radially outwards. So because if it's not radially outwards, that would spoil the spherical symmetry. So the electric field must be radially outwards. Radially outwards is a spherically symmetric distribution of the field. So direction is radially outwards. And what about the magnitude? So we can also conclude something about the magnitude of the electric field. The magnitude must be such that the electric field is a function of r only. So let's try to let's make sure we understand this. So I'll just draw another diagram here just to understand this point. So here's a sphere, and there is charge on the sphere. And suppose the electric field at a distance of maybe 2 meters from the center, the electric field is radially outwards and has a magnitude of maybe 10 newtons per coulomb. I'm just completely making up these numbers. Now, at the same radius of 2 meters over here, the electric field has to have the same magnitude, 10 newtons per coulomb, as long as the radius is still 2 meters, right? So at any radius of 2 meters, the magnitude has to be the same. Why does it have to be the same? Because if it were not the same, suppose over here it was 100 newtons, suppose it was something different over here, that would completely spoil the spherical symmetry. Because if your friend challenged you to to see if you can tell if the sphere has been rotated, all you had to do is just remember where the 10 newtons per coulomb is and where the 100 newtons per coulomb is. And when you open your eyes after the sphere has been rotated, you can just tell that it's moved, that point has moved, right? So at a given radius, to preserve the spherical symmetry, the electric field has to have the same magnitude and it has to be radially outwards. That makes sense? The magnitude does not have to be the same at all radii. Like for example, at 1.5 meters, somewhere over here, if this is 1.5 meters from the center, the electric field does not have to be 10 newtons per coulomb. We'd in fact expect it to be maybe a bit stronger because you're closer to the sphere. So maybe over here it's 15 newtons per coulomb. I'm just again making up the numbers. But that would mean that at any radius of 1.5 meters, it has to be again 15 newtons per coulomb. That clear to all of you? Yes, Naomi, did you have a question?
Yes, my question is there any way you could just quickly show us how it would be different if there was an excess negative charge?
Yeah, everything would be the same. A very good question. Everything would be the same, just the electric field would be pointing radially inwards. That's the only difference. So if you have excess negative charge, the only difference is that the electric field at any point would be pointing radially inwards. But everything else we said about the electric field will be the same. That makes sense? Very good question. All right. So the electric field would just be pointing radially inwards. All right. And we are about to draw field lines now. So for positive charge, the field lines would have an arrow pointing outwards. And for negative charge, the field lines would have arrows pointing inwards. That's the only difference. All right. So we made two very important conclusions about the electric field. The electric field's direction, when you have spherical symmetry, is radially outwards, and the magnitude depends only on the radius. So at a given radius, the magnitude is fixed. That clear to all of you? All right, you can combine these two facts about the electric field and write them in a very convenient and compact way. The electric field vector has a magnitude which only depends on r. So I'm writing that as E function of r. And its direction is in the radially outward direction. That clear to all of you? So writing this little equation summarizes the two sentences above that. Okay, any questions so far? All right, so that's what we concluded from spherical symmetry, that the electric field must have this form. We have no idea what this function is, E function of r. Ultimately, that's what we want to find out. What is the electric field at a distance r from the sphere? That's our ultimate goal. That's what we want to calculate. All right. So now that we figured this out, now it's time to think about field lines. So let me just make a new diagram. So here's our sphere again, same sphere. We have some excess positive charge on the sphere. And we know that the electric field is radially outwards. So now what do the field lines look like? You know that the field line arrows are just obtained by joining the field lines are obtained by joining the electric field arrows. So the field lines will just be radially outward lines. So lines sort of going outward like this. Okay. So these will be the field lines. And for positive charges, the field lines will be going outwards because field lines come out of positive charges. And if you had excess negative charge on the surface of the sphere, the field lines would just be going inwards because field lines always terminate on negative charges. And so that's it. So those are our field lines. So that brings us to the next question. I mean, that concludes the first four questions. So draw the field lines accordingly. The next question is, we are interested in finding the electric field at a point at a distance r from the center of the sphere. That's where we want to find E. Our goal is to find E as a function of r. So we want to find the electric field at a distance r from the center of the sphere. So how do we do that? What we do is we draw a Gaussian surface passing through that point. So the Gaussian surface that I'm going to draw, that's a very important choice, what Gaussian surface you draw. So when you have spherical symmetry, what shape do you think the Gaussian surface should have? So what shape of surface should I choose? Do you think, if I have spherical symmetry?
A sphere.
Yes, absolutely. It should be a sphere. Okay. So again, this circle that I drew, these circles are all spheres, right? So this is a sphere which surrounds the whole charge distribution. This is our Gaussian surface, right? And we drew the Gaussian surface through the point where we wanted to find the electric field. So we made the Gaussian surface at the same radius. So we are interested in finding the electric field at point P. All right. Now, all we have to do at this point is just evaluate Gauss's law over this Gaussian surface. So Gauss's law, so we'll write this equation many, many times today, states that the flux of the electric field over the Gaussian surface, which can also be written as the surface integral of the electric field over the Gaussian surface, so these two mean the same thing, is equal to the charge enclosed by the Gaussian surface divided by epsilon 0. So that is just Gauss's law, right? So all we have to do is just evaluate this surface integral and then solve for the electric field, right? Okay. Now you'll see that evaluating the surface integral becomes extremely easy because we made a good choice of Gaussian surface. If we had chosen any other Gaussian surface, the integral would have been next to impossible to do. But guided by the symmetry of the problem, we have come up with an excellent choice for a Gaussian surface. That makes the integral easy to do. Okay, so we're going to proceed with this. This is what we're going to try to evaluate now, surface integral E dot dA. And this will be very, very, very similar to what we did yesterday. So it's hardly anything new here at all. So first we want to write down the E. The E, we concluded, must have this form. It's some unknown function of r, which we ultimately want to find out, multiplied by r hat, because it's radially outwards. That makes sense? All right. And what about dA? dA, we had done this yesterday. dA means a small patch of surface taken on the Gaussian sphere, Gaussian surface. So just maybe this little patch over here on the spherical surface. So it would point in the radially outward direction. Let's remove these field lines to reduce the clutter. So this dA can be represented by this vector. it points radially outwards, and its magnitude is just whatever the area of that tiny little patch is. So that's the dA vector, right? So you can write the dA as dA, which is its magnitude, multiplied by a unit vector in the radial direction. That makes sense? It's just what we did yesterday. All right, so now that we have E and dA, the vectors, we can find E dot dA. So we did this yesterday as well. So the scalar stuff just goes for a ride. So you have E of R dA. This is just the scalar stuff. And the dot product is between R hat and R hat. And so what is R hat dot R hat? We did this yesterday.
1.
It's just 1. So we worked this out yesterday. So this is just 1. And so E dot dA just becomes E of R dA, right? And that is what we need to calculate the surface integral over. So we have to do, so we have to calculate surface integral E dot dA. That's the left-hand side of Gauss's law over our Gaussian surface, which is going to be equal to surface integral E of R dA, because we just simplified this E dot dA into E of R dA with all the vectors gone, over the Gaussian surface. Remember that this surface integral is being done over our spherical Gaussian surface, our green surface here. Now, since the electric field is spherically symmetric, it has a fixed value at a given R, right? So that means the electric field has the same magnitude over the entire Gaussian surface because it's a sphere, right? Its R is fixed everywhere, and E only depends on R, which means that for this particular Gaussian surface, E of R is a constant, right? Because we are evaluating it over the surface of a sphere. So that implies that I can just pull out the E of R because it doesn't depend it doesn't depend on R. I mean, it has a fixed value for that particular R. So it's a constant as far as this integral is concerned. I can just pull it out. And so I have E of R, and then I have to integrate dA over the Gaussian surface. Everybody clear about that? And now you can see why choosing a good Gaussian surface is important, because if I had any other surface that I was using as a Gaussian surface, then this E of R would not be a constant. Because it would, for different values of R, you would have different values of E, so it would not be a constant, and I would not be able to pull it out of the integral. But for
I
a
have a
sphere,
question.
yeah.
Because the problem says a charged metallic sphere of radius capital R, at
Yeah.
that point, could you just change it to a capital R?
No. Capital R, very good question. Capital R is this radius, right? That's the radius of the sphere. But we are evaluating the electric field at little r. Little r is the yellow line. So that's some arbitrary distance from the center of the sphere. And we've drawn the Gaussian surface through that point. That makes sense? So
Got
we are
it,
working
yes.
with the green surface over here. Very good point.
Okay,
We're
thank
working
you.
with the green surface over here. And so we are doing the integral over the green surface. All right, everybody clear about that? Any other questions? All right, so now all we have to do is add up. So surface integral dA, we talked about that in the last class. Surface integral dA, what does that mean? It means adding up the areas of all these little patches. You can see one of the dAs marked over here, like this patch, this dA. So if I add up all the areas of all such little patches over the entire green sphere, what am I going to get? The full area of the green sphere, right? And what is the formula for the surface area of a sphere?
Is it 6A squared?
No, it's 4 pi r squared. So the surface area of a sphere has
Oh,
the
sorry,
formula
that
is
was a
4 pi r
cube.
squared. Yeah. So yeah, for a sphere, the surface area of a sphere is 4 pi r squared. And so this is just going to be equal to E of R times 4 pi r squared. That makes sense? All right. So now that we've seen this calculation, you don't have to do all these steps. So you can keep this shortcut in mind from here to here. So if you have if you're evaluating this surface integral, you have a spherically symmetric charge distribution. spherically symmetric E. A spherically symmetric charge distribution means that you have a spherically symmetric electric field, and you have chosen a spherically symmetric Gaussian surface. So if these two things are true, then you can jump straight from surface integral E dot dA. It just works out to E of R times 4 pi R squared. That makes sense? So I just wanted to show you the steps to show you that it's not some great mystery, but you can just use this shortcut. So if you have a spherically symmetric electric field and you have chosen a spherically symmetric Gaussian surface the right way with, then the surface integral, the value of the surface integral just becomes E of R times 4 pi R squared. And we have worked out the full left-hand side of Gauss's law now. So let's go back to Gauss's law again. So Gauss's law was that surface integral E dot dA over our Gaussian surface, which we have fully worked out now, is equal to the charge enclosed divided by epsilon 0, right? So the left-hand side we already worked out. It's E of R times 4 pi R squared. And the right-hand side, let's think about that now. So let's look at our Gaussian surface. That's the green sphere. Can you tell me what charge, and the charge on the sphere is Q. So what is the charge that you see is enclosed by this Gaussian surface?
Excess positive charge.
And what is the amount? You're absolutely correct. What is the amount of that? What symbol tells us the amount of positive charge? It's Q, right? That's what the problem has told us. It's Q. Yeah, very good. So the charge enclosed by the sphere is just the excess positive charge. That makes sense? And so our Q enclosed is just Q divided by epsilon 0. And so Gauss's law, with a good Gaussian surface, Gauss's law reduced to this extremely simple algebraic equation. And from here, you can just solve for the electric field. E as a function of R, which is what we wanted to find, turns out to be Q divided by 4 pi epsilon 0 R squared. And that's the final answer. So the electric field at a distance R from our charged sphere is given by Q divided by 4 pi epsilon 0 R squared. That clear to all of you?
So in most of these problems, will you be giving the electric field in like a function form?
You'll have to find the electric field as a function form. That
Okay.
makes sense? Yeah. So you will be given the charge distribution in some form. You'll be given, we haven't used rho yet, but you'll be given what the charge distribution is. And using Gauss's law, you'll have to find the electric field produced by that charge distribution. And in order to do that, in order to be able to evaluate the surface integral, you will just have to choose a good Gaussian surface, which will be completely dictated by the symmetry of the problem. So when you have spherical symmetry, you're going to choose a spherical Gaussian surface. And if you have cylindrical symmetry, you're going to choose a cylindrical Gaussian surface. We'll see that later on. But what happened in this problem was that we were given a charge distribution. The charge distribution was basically the charge spread out on the surface of a sphere. And we wanted to find the electric field at a certain distance from that charge distribution. And we were able to do that using Gauss's law. The other way we could have done it is using Coulomb's law, which is what we did in chapter 21. And I told you that would have been horrendously difficult. Whereas with Gauss's law, it's literally 2 lines of algebra gets you the answer. That clear to all of you? All right. Now let's, okay, so we covered all the steps here. We discussed all this. We drew the field lines. What would be an appropriate Gaussian surface, a sphere? And how do we calculate the left side of Gauss's law over this Gaussian surface? We did that. And then how do we calculate the net charge enclosed inside this Gaussian surface? That's just, our Gaussian surface surrounds the whole sphere. So the charge enclosed in the Gaussian surface is just the charge on the sphere.